Okay. So our next speaker is going to be Deepesh Singh, who's going to tell us about maximum number of points on an algebraic set over finite fields.
Thank you everyone for being here. So I'd like to set up this problem that gives some motivation in terms of coding here. So firstly, we start with a finite field FQ, and a chord of length n is simply any linear vector subspace of FQ to the n. So we have a distinguished basis in FQ to the n. Now, given a chord, its support is defined to be the set of indices from 1 to n, for which we have at least one vector in our code whose ith coordinate is not zero. So the support are those indices for which like some vector is non-zero I coordinate within our code. And then the rth generalized Hamming weight is we go through all the r-dimensional subcodes of C. So C itself was a vector subspace, and we look at all r-dimensional subspace of C and look at the smallest size of C. It's called the rth generalized Hamming weight. If you take R to be 1, that is simply known as the Hamming weight. Then we'd be looking at Reed-Muller codes. So in order to define Reed-Muller codes, we start with the space of polynomials in m variables of degree at most p. So these form a vector space, and then we let n to be the size of the affine space, which is simply q to the n, and we enumerate the points in the affine space as p1 to p sub little n. And then in order to get the Reed-Muller code, we simply evaluate each polynomial at all the points in our affine space. So there's a code of length n, and each coordinate here corresponds to one of the point in the affine space. Now, in order to compute these generalized Hamming weights of the Reed-Muller code, so firstly, we assume that Q is at least D. This is to ensure that the map from polynomials to functions is injective. So we'd always assume that Q to be large, sufficiently large for our purposes. And then, r-dimensional subcode corresponds to a vector subspace of polynomials. So each vector corresponds to polynomials. So we look at r-dimensional subspace of a vector space of polynomials. And then the support is those coordinates, so those points of the affine space, for which at least one vector is non-zero. So the complement of the support would be the zero set of W, the FQ rational points of zero set. And so the support is the complement of the zero set of W. And the rth generalized Hamming weight, this was the smallest support. So that corresponds to the largest zero set. It corresponds to the zero set with the most number of FQ rational points among all the r-dimensional subspaces of these polynomials. Now, we give a notation here. So this ERDM with this superscript A. This is the largest number of FQ rational points we can have on the zero set of W, where W varies over r-dimensional subspaces of this polynomial ring of degree at most. And then there's an exact formula for ERDM. Now to understand that, we start with this omega dm. This is the collection of all the tuples of non-negative integers that sum up to t. So there's finitely many such tuples. And we order these based on lexicographical order. And so we order is finite many in lexicographical ordering, and we pick the rth largest element here. So it would be some tuple beta 1 to beta m. And we form a polynomial in Q. So we take powers of Q with coefficients corresponding to these beta i's, which is the rth largest tuple in lexicographic ordering. And the theorem by Heinen and Pelikan was that if Q is at least t plus 1, then the exact formula for ERDN is precisely this polynomial in Q. And then we look at the projective version of this problem. So there are these projective three-polar codes for which we start by considering polynomials in m plus 1 variables, and we look at homogeneous polynomials of degree d. And then this time we let n to be the size of the projective M space over Fq, and we enumerate the points of projective M space P1 to P sub small n. And then the projective real molar code is again defined by evaluating each polynomial at all the points. Now, you should note here in the projective M space, the points are defined up to multiplication by a constant. So, like we pick a representative, and this code here sort of depends on which representative we pick, but up to isomorphism, it's the same code. Then we can again look at the rth generalized Hamming weights of these. So again, the subcodes of the projective real molar codes correspond to subspaces of this polynomial vector space. And the support is again complement of the vanishing set. And so the rth generalized Hamming weight is the smallest support, which means corresponds to the largest vanishing set. So this motivates, so we make a notation for this here. So ERDM is you look at the space of degree d homogeneous polynomials in m plus 1 variables. Look at all r-dimensional subspaces and look at the largest vanishing set among those. And so this is the main problem that we were working on, is to like get exact formula for this, the projective version of this ERDM. Here we make this notation. Pi m is the size of the m projective space. So there was this conjecture by Saffman and Bogulavsky back in 1997, in which they conjectured that, so they again, the WRDM was the rth largest tuple in lexicographical order. They take L to be the first non-zero coefficient, and they again form some kind of a polynomial in Q. Looks a bit more complicated, but the coefficients are again related to these beta i's, slightly more complicated polynomial. And they conjectured that this was the exact formula for ERDM. Then some cases of this conjecture have been proven. So the case R equals 1, in which case you have a single polynomial. So this is asking for the maximum number of points on a hypersurface. So this was proven independently by Serre and Sorensen. Then the case R equals 2, when you have two polynomials, this was proven by Bogulavsky. And Zanella had explicitly computed the degree 2 case of any number of polynomials in any number of variables. And then Datta and Khodpare, they prove this conjecture for R up to m plus 1. However, they disprove the conjecture when R is bigger than m plus 1. They show that the conjecture formula is too small. And they came up with a new conjecture formula for ERDM. So we call this the third party, the Wheelan conjecture. It looks a bit more complicated. So we again fix ND, we fix some R. So M was the number of variables, D is the degree, R is the dimension of the vector subspace. We assume Q to be at least D plus 1. And then they subdivide this interval based on M. So they do M plus D choose D minus M plus D minus L choose D. And so the R would uniquely determine a L for which R is in a particular smaller interval. And based on this L, then they put J to be R minus this thing. And they form a polynomial in Q. So the coefficients are again related to those beta 1 to beta m, those tuples. The difference is that they reduce the number of components. So previously, this was in dm, so we had m plus 1 elements in the tuple. Now they've reduced the number of elements in the tuple to m minus l plus 1. And the L was determined on which subinterval R is in. And then if we compare the two conjectured formulas, they both agree for R being at most m plus 1. This case was proven by Murpade and Datta. But the two formulas differ when R is bigger than m plus 1. Then they prove some more special cases. They prove the degree 1 case, they prove the one variable case, and then they extended the case from m plus 1, which is m plus 1 choose 1, to m plus 2 choose 2. So they prove this for small values of R, and then they also prove this for large values of R, for the last d plus 1 values. So this corresponds to L being m or m plus 1 in the previous notation. And they also prove that, so for small values of R and large values of R, we have the exact formula has been proven. And for all the other values, they show that the conjectured formula is at least a lower bound for ERDM. But to show that it's an exact formula for the middle values of R remains unproven. So that brings us to our result, myself with Dave. So what we do is we prove that, so we allow R to be any number in the entire range from 1 to m plus d choose d. And we require Q to be large. I'll get to what this quantity represents. But assuming, so we allow all R to be in any range, and assuming Q to be sufficiently large, we prove that the formula conjecture by Murpade and Datta is the exact formula for ERDM. And here, based on R, we determine this L and C based on which subinterval R is in, and we'll see the significance of these numbers, L and C. So our result, so our method differs from the previous results because most of the previous results were all proven using very combinatorial techniques, and they did not give much geometric insights into the vanishing set of tuples, whereas our method is much more geometric. So we start by asking a simpler question. So you vary W through all R-dimensional subspaces, and we ask what is the largest that the dimension of the vanishing set could be. And so here, myself and then we show that the number L that was appearing earlier, based on the which subinterval R is in, this L is the largest 4 dimension. So sorry, smallest 4 dimension. So largest dimension of the vanishing set of W can be is M minus L, where L is determined by which subinterval R is in, which range R is in. That's great. That gives us some geometric insight into this vanishing set of W. And the next thing we ask is for the degree. So, we pick R to be in this subinterval corresponding to L, and W varies through R dimensional subspaces, for which we have dimension M minus L. And then we ask how big can the degree of the vanishing set be. And so we show that the degree is, in order to get the highest degree, you have to subdivide this interval based on C. And based on which subdivision R lands in, that determines the C from 1 to D, and that's the highest degree. And both of these results were proven using the technique of Hilbert polynomials, where we show this proposition where we pick X to be any projective subscheme of EM F2 bar, and we fix its dimension and degree. And S of X is the coordinate ring, and if we put a subset of T, we mean the degree of the dimension of the degree T component. And what we show is inductively we find a lower bound on the dimension of this STX, depending on K and C. So once we fix the dimension of X and the degree of X. And the way the result follows from there is because if you look at the vanishing set of W, then we know that if X was the vanishing set of W, then we know that this ideal of X contained W. So we know that there are a lot of things in the ideal, so that puts a lower bound on how big the dimension of S of X can be. And so that allows us to, in terms of R, to get a bound on this dimension and the degree. And so, however, knowing the dimension, the vanishing set of W need not be equidimensional. It can have irreducible components of different dimensions. And knowing the dimension of X and the degree of X, that only gives us information about the top dimension. The lower dimensional components don't contribute to the degree. So next we look at the lower dimensional components of X. So we make this notation, X is some algebraic set. Then we look at all the J dimensional irreducible components of X, and the sum of the degrees of all the J dimensional irreducible components, we denote it as degree sub J of X. Then the result we show is that if you pick homogeneous polynomials, any number of irreducible polynomials of, any number of homogeneous polynomials of degree at most D, and then take their vanishing set. Then once you look at the lower dimensional degrees, they themselves can get bigger and bigger. But if you we assign these weights of D to the J. So as you go into a lower dimensional degree, you get a higher term in the denominator. Then this weighted sum remains bounded by 1. And so this gives us a way of bounding the degrees of the lower dimensional components, with which we can bound the number of points in the lower dimension. So as a corollary, we obtain that X is as above, the vanishing set of some number of polynomials of degree at most D. And we take Y to be the union of the irreducible components that have dimension at most M minus L. Then we show that the number of FQ rational points of Y is at most D to the L, and this high M sub L is about like Q to the N minus L. So this gives us a way of bounding the number of points on the lower dimensional components. And we know the degree and the dimension of the highest dimensional component. So still requires some work, but we can put all of this together, and assuming that Q is sufficiently large in terms of this L and C, which corresponds with dimension degree, we can show that the conjectured formula by both Pareto and Whelan gives us an exact formula. PRD. That brings me to the end of the presentation.
Thank you. So are there any questions for our speaker? Okay, if not, let's thank our speaker again.